Good morning, guys. It's Monday, October 12th. And how are you doing? Can you hear me?
Yes, we can.
Good, thank you. Good, thank you. And today we're going to finish our chapter 6. Hopefully we'll have a better day today. I uploaded a better version of the lecture on Friday on YouTube. So please consult that. It's at the very end when I sort of kind of collapsed. It's I want to show you one slide that I was going to show you on Friday. Okay, so we were talking about this K-cat over Km value, right? This ratio. And I told you that it's a very important ratio because if you think about it, so K-cat is the reaction constant, right? So it's how fast the enzyme catalyzes the reaction. But Km, remember Michaelis constant, is a measure of the affinity of the enzyme for the substrate. So both of these are important, right? And so the lower the Km, the higher the affinity of the substrate for the enzyme, and obviously the higher the selectivity, right? So the so the enzyme will be highly selective in choosing the right substrate over a C. Think about the cell, right? Think about the cell. There are thousands, tens of thousands of large molecules. There is like hundreds of thousands of small molecule metabolites. It's like a soup of stuff, right? And so the enzyme has to select just the right substrate, and the Km value is very important from that perspective, right? So it's also a matter of how the enzyme chooses its substrate, and once it has chosen a substrate, Kcat is how fast it will catalyze the reaction. And so that's why we say that the ratio of these two is the measure of enzyme efficiency, okay? And one can be large, the other can be not too small, or the other way around, but the ratio will is what we should look at. So we quickly looked last time at acetylcholine esterase. So I told you that, or you told me actually, that acetylcholine is a neurotransmitter, right, which is released in the synaptic cleft from the presynaptic neuron, and it works on, and it acts on the receptors of the postsynaptic neuron. And once the signal is transmitted, then there is an enzyme in the synaptic cleft known as acetylcholine esterase. So it will break down acetylcholine back into the back into the colon, which will be reabsorbed into the presynaptic neuron. And you can see here, so it's the combination of Kcat and Km, which gives us such a high number, 10 to the 8. Now, if you look at, let me choose another example. Here, a catalase, so the enzyme that breaks down hydrogen peroxide. Now, Km is actually not very low, right? In fact, so this enzyme doesn't have high affinity for hydrogen peroxide, but Kcat is extremely high. And it's the combination of the two that still gives it a very high ratio of Kcat over Km. And so there is what's known as the upper limit for catalytic efficiency, right? So it's 10 to the 8, 10 to the 9th. And the reason for that is diffusion. The reason for that is diffusion. So just think about, so the enzyme is swimming somewhere in a cell, right? and the substrate is somewhere in some other part of the cell, and the substrate just never makes it into the area where the enzyme is. And so it doesn't matter how efficient your enzyme is, the substrate will not be converted to the product, right? And in fact, the enzymes have evolved to even to kind of to sense the substrate when the substrate is nearby. So let's say the substrate swims nearby, and the enzyme has a ability to attract the substrate towards itself, or the substrate can bounce on the opposite at the enzyme, but on the opposite side of the active site. And the enzyme still has a way to grab the substrate and pull it all the way around towards the active site and make it undergo reaction. It's amazing how these enzymes evolved, right? So even though there is nothing on the opposite side, just amino acids, and yes, these amino acids are just the right amino acids to grab this substrate and bring it to the active site. So this is a highly investigated area of enzymology. We still don't quite understand how the enzymes can function like that. But they have to because of this diffusion limit, right? Because if you think about it, if it's only that the substrates which happen to be in the area of the active site, if it's only those substrates that undergo the reaction, then the enzymes would be highly inefficient.
Go over real quick again what a low kcat and what a low km is equivalent to. You said low kcat.
So you want high kcat and low km.
Okay.
For high catalytic efficiency, and that's what it for acetylcholinesterase. That's what it is.
So with the high kcat, what do you get?
So high kcat, so that's the reaction rate. So you want the reaction rate to be high.
Okay, right? So a high kcat is equivalent to high reaction rate.
Yes.
Okay.
Well, kcat is the reaction constant. Remember, we also talked about this in terms of a turnover number. Yeah.
And a low km is equivalent to
high affinity of the substrate for the enzyme.
Okay, thank you.
Mm-hmm. All right, so let's talk about inhibition now. So obviously, we have tens of thousands of drugs on the market, right? And majority of the drugs work by inhibiting enzymes. And actually, I take it back. A large proportion of drugs, I don't know, I need to check on whether it's majority or not. The large proportion of drugs work by inhibiting enzymes. And so there are what's known as irreversible inhibitors. So we'll talk about those in a moment. Right, so here is irreversible inhibitors, basically molecules which will inactivate the enzyme, right? So they will react covalently with one of these amino acids at the active site and kill it, basically. So one molecule of inhibitor is sufficient to kill one molecule of the enzyme, extremely efficient. Now for reversible inhibitors, so those come and go, and usually these are structural analogs of substrates or products. So in other words, they look like substrates or they look like products, and the active site gets confused. The active site thinks that these inhibitors are actually substrates and accepts them with open arms. And so these reversible inhibitors occupy the binding site, and then the substrate cannot come in anymore, right? The substrate cannot come in anymore, and no reaction happens. And so the enzyme basically will not be killed, but it will be slowed down, right? So basically the enzyme will slow down until this inhibitor leaves, and then the substrate can come in and finally the reaction can occur. So yeah, so reversible inhibitor can bind to the free enzyme and prevent the binding of the enzyme. And also, we will talk about the fact that reversible inhibitors can bind to a different site on the enzyme, right? Even though, let's say, substrate is already bound at the active site, but the inhibitor can bind to a different site. We call it allosteric site. and it'll still prevent the reaction. So we'll talk about those as well. All right. So there are three kinds of reversible inhibitors. So let's look at each of them. So first of all is competitive inhibition. Competitive inhibition is when the inhibitor competes with the substrate for binding. It binds to the active site. Okay, so let's say this is competitive inhibition. Enzyme plus substrate forms the enzyme substrate complex. This dissociates into enzyme and product, but there is this inhibitor, I. The inhibitor I can compete with the enzyme, can compete with the substrate for the binding site or the active site on the enzyme, okay? Enzyme with a specific dissociation constant, it can form inhibitor enzyme complex, EI. So graphically, this is shown like this. So this is the active site, right? So the active site can be occupied by the substrate, like so, or the binding site can be occupied by the inhibitor, like so. And so what we will notice is that when this happens, there will be no change in the Vmax. So this is one of the key observation. If your inhibitor competes with a substrate and it's a competitive reversible inhibition, then the maximum rate will not be affected. All you need to do is to add more of the substrate, and eventually the larger quantity of the substrate will outcompete the inhibitor for this binding site, and the reaction can still reach the Vmax. And there will be increase in Km, and increase in Km is because inhibitor competes with the substrate, right? So you need more substrate to bind at the active site for the reaction to occur. And so the effect of that is almost like the substrate has lower affinity for the active site. It doesn't. It's just the reason why it doesn't bind so strongly is because there's always this inhibitor sitting around and preventing it from binding at the active site. So let's look at the Lineweaver-Burke plot. And so this is how this would look like, this competitive inhibition. Maybe I should draw let me draw, I don't think I have that here. Let me draw the Michaelis-Menten equation, how it's gonna look like. Vmax substrate alpha Michaelis constant plus substrate. So you see where this alpha is, right? So alpha is going to be positive number. And basically the effect of this alpha is that it will increase the this term here, the term where Km normally resides, right? So basically apparent Km will be larger. And if the Km is larger, remember what that means? That means the affinity of the substrate for the enzyme is lower. And it's only apparent affinity, just because of the competition with the inhibitor. Okay, so if you take the reciprocal of this, you end up with this Lineweaver-Burke plot, okay? And this alpha ends up in the slope term, okay? And you can see here, as you add the inhibitor, you increase this value of alpha. You increase the apparent Michaelis constant. And so the slope changes, the slope keeps increasing as you increase the amount of the inhibitor, right? And as the slope changes, this ratio increases, and but one thing to notice is that the intercept, y-intercept, which is 1 over V max, that does not change, right? So this point here has not moved, which means that the Vmax, no matter how much inhibitor you apply, the Vmax will not change, and you can still reach the Vmax by simply adding more and more substrate. So eventually, if you keep adding more substrate, it will outcompete the inhibitor, and you can reach the Vmax. You can also see it here, right? So if you add, so if this term, the substrate concentration becomes so large that this term alpha Km becomes too small compared with the substrate concentration, then the V naught will equal V max. You will just simply ignore or just cancel out two substrate concentrations, and V naught will equal V max. All right, so this is a case of competitive inhibition. Any questions? All right. So in a typical problem, what you will see is that you will be given a set of rates versus set of substrate concentrations, and now you have three unknowns: Km, Vmax, and alpha, right? And so but you have three data points. You have a data point in y-intercept, x-intercept, and the slope. And three unknowns with three data points, you can get all three of them. All right, uncompetitive inhibition. Sorry?
Well, what you just said about obtaining the unknowns.
So you have three unknowns, correct? Km, Vmax, and alpha?
Yeah.
And then you have three data points. So from three data points, you can get three unknowns. You have y-intercept, x-intercept, and the slope.
So like on the exam, would we be given a problem like this, and we'd be given like parts of the unknowns, and then have to like find Vmax or something like that?
Yeah. Well, I think again, there will not be so much math on the exam, mostly conceptual stuff. But on the exam, what I may ask you is the kind of the meaning of what this is, and or how you go about solving this or something. But I will certainly not make you go through taking the reciprocal of every number that I give you, and but you have problems like that in Sapling. You have problems like that in Sapling, so practice Sapling, and you should be fine.
So you said one of the ways that we might be quizzed on this or tested on this is that we would have to solve for this equation. Like, by that, do you mean like how it's derived?
How this is derived?
Well, you said that one of the ways that you might test us on it is like solving for this. Not finding each part, but you said overall solving for it, and I was confused by what you meant by that.
No, as long as you know how to go about it, and I mean that's all I kind of need from you as far as the test. But there are a couple problems on Sapling which will actually make you go through this, where you will be given substrate concentrations and rate concentration and rates, corresponding rates for each substrate concentration. In fact, I put something in, remember, from the lecture on Friday. you asked me to throw in some problems in a discussion, so I did. So if you guys look at those, provide me your solutions, and then maybe we can start a discussion on that basis.
Where'd you provide those? In the discussion board?
Yeah, there's a discussion on a discussion in the discussion board. I throw in some problems. One of them is actually deals with the Lineweaver Burke plot. So so if you can look at it and try to solve it and provide me a solution, and we can start a discussion on that basis. Maybe I can ask you some questions based on your solution, and okay. All right. All right, uncompetitive inhibition. So here it's a little different case. So this is usually the case of allosteric enzymes. So here the enzyme and substrate bind to form the enzyme substrate complex, okay? And only then the inhibitor will come in and bind to the enzyme substrate complex. And usually this will be at, obviously it will be at a site which is different from where the substrate binds, because the active site is already occupied. So let's look at that. So now you have two sites. So this is the site where the substrate will bind. And this is the site where the inhibitor will bind. And the inhibitor, by binding at this site, will slow down the reaction. So you can see here, there will be decrease in Vmax. Decrease in Vmax. And so for Km, it says here apparent decrease in Km, but I need to think more about it. So when you, so decrease in Km means that the affinity of the substrate for the enzyme increases. And so the inhibitor, I guess when the inhibitor binds to the enzyme, that stabilizes the inhibitor the enzyme substrate complex in a way. Well, let's think more about it. Let's think more about it, because I'm not totally sure if it always decreases the Km, or there'll be situations when the Km will increase. But that's not really important for us. What's important for us is to, again, to understand the how Michaelis-Menten equation changes. Okay, let's look at that. And let me draw this. V naught Vmax substrate concentration. So in this case, it's going to be alpha prime. Alpha prime.
Professor?
Yeah.
Not to really jump back, but could you talk about where alpha comes from?
So again, so alpha, yeah, we are going to be jumping back. So basically what we need to do, oops. Basically, so I mentioned to you that when the inhibitor competes with the substrate for the active site, right? So there are fewer sites available on the enzyme for the substrate to bind, because the inhibitor is occupying them, right? Look, so basically the enzyme is taken away by the inhibitor to form inhibitor-enzyme complex. So the substrate doesn't have that many sites left on the enzyme. And so the net effect of that is apparent increase in Km. So in other words, the apparent increase in Km, in other words, the apparent increase in the decrease in the affinity of the substrate for the enzyme, just because there's less of the enzyme. And so you're forming less of the enzyme substrate complex. So in other words, this equilibrium will be shifted to the left, right? Remember Le Chatelier principle? If the inhibitor pulls this equilibrium down, then this equilibrium will be pulled to the left, and so less of the enzyme substrate complex will be available. Correct? Does it make sense?
Yes.
And the apparent result of that is that there's the affinity of the enzyme towards the substrate has decreased, and that results in an increase of Km. Remember, Km is the measure of the affinity. And that's why we introduced this alpha to show that Km now is going to be larger, right? And the Km is going to be larger and larger, larger, depending on how much of the inhibitor you add.
Okay, that makes sense. And so in comparison to uncompetitive inhibition, I think you were getting to how the alpha affects it because they're not competing for the substrate, right?
Yes, so there's no competition for the substrates. In fact, substrate binds first. And so, but there will be a change in a Vmax. So let's look at the Michaelis-Menten equation. So you can see the Km term kind of stays the same, right? Because the substrate binds first. It's not affected by the binding of the inhibitor. And so if you take the reciprocal of this, the alpha prime now ends up in this portion of the Lineweaver-Burke equation, right? And you can see what happens here. The slope, this is the slope. The slope doesn't change. That's why you get all these parallel lines. As you increase going from alpha prime equals 1, alpha prime goes to 1.5, goes to 2, right? They all parallel lines because the slope does not change. But what will change is the y-intercept. Y-intercept, right? Because the alpha prime ends up now in this portion of the equation. And so you keep climbing. First you're here, then you're here, then you're here, right? And make sense? So this is the case of uncompetitive inhibition. And so this is usually the situation when you have allosteric inhibition, I guess. So the inhibitor binds at a site which is not at the binding site. And finally, there is a situation where both types of inhibition occur. It's known as mixed inhibition. So enzyme and substrate can bind with the inhibitor to form enzyme inhibitor complex and prevent substrate from binding, right? Or enzyme and substrate bind, and inhibitor binds after that to form this what's known as a ternary complex, enzyme substrate inhibitor. So you can see here, it's like a square, right? So the enzyme binds the substrate, binds the inhibitor, or the enzyme binds the inhibitor first, and then binds the substrate. And so the inhibitor will bind to what's known as a regulatory site, right? Also known as allosteric site. And in this case, it will inhibit both the substrate binding and catalysis. Okay, so let's look at now at, so the Lineweaver-Burke plot is actually now the combination of both the competitive and uncompetitive. Vmax. And so now both alpha and alpha prime prime play a role. And you can see here, so alpha is now part of the slope, and alpha prime is now part of the y-intercept. And you can see here, as you increase the inhibitor concentration, you increase the slope, and also you also increase the y-intercept, right? So the point of convergence of all this is not on the y-axis anymore, it's to the left of it, to the left of the y-axis. And so this will be the case of mixed inhibition. And this type of inhibition is, I guess, would be, now, I don't want to say it's less common. Let's go back to this. So well, so the inhibitor has its own site. Yeah, I need to look into this. How common? How common? I'll put in the discussion section. How common each type of inhibition? Okay. Each type of inhibition. All right, so now let's look at some specific, in the remaining, 20 minutes, let's look at some specific mechanisms, how enzymes accomplish their reactions. So let's look at digestive enzyme, chymotrypsin first. So this is a dietary protein. And basically proteases are enzymes which cut peptides at specific locations on the peptide backbone. And so this particular protease, it can cleave the peptide bonds adjacent to aromatic amino acids. So you can see here you have tyrosine, right? You have tyrosine, and so it's aromatic, right? And so we have a peptide bond like that, and it's going to be cleaved between carbon and nitrogen. So this is the carboxyl end, this is the amino terminus. And so the enzyme, now this is a little harder to see in this ribbon projection, but when you identify some specific amino acids, it's a little easier to see. So what's important for us is this catalytic triad. Catalytic triad consisting of aspartate, histidine, and serine. So we will see this mechanism on the next couple of slides. This is a very common arrangement of amino acids in proteases, where you have aspartate, followed by histidine, followed by serine, which, as we will see, increases the nucleophilic power of serine. And also serine and glycine, they have this amidic NH from the peptide bonds, and these form what's known as oxyanion hole. Oxyanion hole. So let's look at that. So let's, so this is, so chymotrypsin is going to be a free enzyme, okay? So here's our catalytic triad. Now, let's say, so aspartate, histidine, and serine are referred to as catalytic triad. And so look what's happening here. So aspartate, which is deprotonated, is a base, right? It will remove the proton from the imidazole of the histidine. Then this nitrogen, now if you think about the electrons, how they shift from one nitrogen to the other. And so the other nitrogen will remove the proton from serine. And so this serine will start gaining partial negative charge. So this serine becomes quite nucleophilic. Then this serine has an NH, and there's glycine that have an NH. So these two together will form what's known as an oxyanion hole. So in other words, basically it's a part of the active site which can stabilize negative charges. And there is this hydrophobic pocket which will be accommodated from the peptide structure. All right, so here's the substrate. The substrate comes in. So let's see where the substrate is. So here's the substrate. There's the backbone of the substrate running across horizontally, right? So the catalytic triads gets engaged. The serine is right here, which has partial negative charge, right? Basically attacks the carbonyl of the peptide, and the electrons are shifting. The electrons shifting towards this oxygen of the carbonyl, and they get stabilized by the hydrogen bonds from this NH and hydrogen bond from this NH. So basically we engage in this oxyanion hole, right? So this oxyanion hole is a important feature of all the proteases because it stabilizes tetrahedral intermediates. All right, so attack occurs, the electrons move, and then once we form the tetrahedral intermediate, this oxygen gets a full negative charge, and it's stabilized by the hydrogen bonds from here, right? And then remember the collapse of the tetrahedral intermediate from OChem2, right? So the electrons come back, and the carbon-oxygen bond, which connects now the peptide to the enzyme, stays, but carbon-nitrogen bond, which was part of the peptide bond, now breaks. And all the electrons come back towards this original aspartate. Toward the original aspartate. So now this collapses, and now we have this transient. Let's write this down, transient enzyme substrate intermediate. Okay, so then we still have to break this ester, right? So the peptide now has to come off the substrate, otherwise we're gonna kill the substrate. Otherwise we're gonna kill the enzyme, right? We want to release the serine. We want to release the serine so that the enzyme can run the same reaction on a different molecule of chymotrypsin. And so here's water. So water comes in and hydrogen bonds to this histidine, right? As the electrons from the nitrogen form a hydrogen bond to the proton, this oxygen is starting to get a partial negative charge. And so the water now attacks the carbonyl. And again, you have this oxyanion hole, which will facilitate this hydrolysis reaction, right? So basically what we're witnessing is the hydrolysis reaction at the enzymatic active site. Basically, we're gonna break down this ester, which is facilitated by the enzyme, right? So the enzyme turns water into beta nucleophile by removing the proton, and it turns the peptide into a beta electrophile by stabilizing the tetrahedral intermediate. So shown here. So this is the tetrahedral intermediate, hydrogen bonds, right? The electrons come back, this, and then the serine would leave. The serine would leave. Will reform the hydrogen bonding with the histidine, and the peptide is now has the free carboxyl residue, right? And the oxyanion hole is released, and then the so this part of the peptide is now dissociates from the active site of chymotrypsin. So final product dissociates, and we reform the active site with the aspartate, histidine, and serine, oxyanion hole, and then the hydrophobic area active for the next molecule of chymotrypsin. You guys have any questions how this works?
I have a quick question about the transient enzyme substrate intermediate. Could you kind of go over that a little bit more?
So transient enzyme. So basically, look, so here's your entire peptide, chymotrypsin, right? Running from the right to the left, this tetrahedral intermediate. When the electrons come back, it's not the serine which leaves. You break in carbon-nitrogen bond. And you form what is shown here. It's the ester. And the ester is is formed between the carboxyl group of the peptide and serine hydroxyl of the enzyme. So this is a transient enzyme substrate intermediate. So it still needs to be hydrolyzed, right? Because if it's not hydrolyzed, it's going to get stuck there, and you're not going to be able to perform the cleavage of the next molecule of chymotrypsin. Does this make sense?
Yes, thank you.
Okay. And in the remaining time, let's quickly go over the lysozyme reaction. So lysozyme is an antibacterial enzyme which destroys the peptidoglycan cell wall in bacteria. And obviously, if you cleave the peptidoglycan cell wall, then the bacteria cannot withstand osmotic pressure. The bacteria cannot withstand osmotic pressure and will undergo lysis. So lysozyme, for example, is present in tears, right? One place it's, let's see. Anybody knows where else lysozyme lives?
Saliva and mucus.
Saliva, that's right, saliva, I was looking for that. All right. So, so here is the peptidoglycan. So here is the glycan of the bacterial cell wall. So this is what's known as a NAM-NAG. So this is N-acetylglucosamine. So this is a saccharide known as NAG, N-acetylglucosamine, and this is N-acetylmuramic acid, N-acetylmuramic acid. So this glycan in bacterial cell wall is composed of these alternating sugars. And so the lysozyme will cleave at this position shown here. Basically, it will break the carbon-oxygen bond. It will break the carbon-oxygen bond, and shown here in this inset, right? So you have two sugars connected by an oxygen bridge, and to hydrolyze it to give you free hydroxyls. So the X-ray structure of the lysozyme with the bound substrate show that this carbon of the sugar that is going to undergo the cleavage is located in between these two key residues. So glutamate 35 and aspartate 52. And so there are two possible mechanisms. There's been a lot of controversy over this, but in one of the mechanisms, let's follow the SN1 mechanism. So first of all, what we're going to do, basically, we're going to break this carbon-oxygen bond. And to do that, we're going to protonate this oxygen with the proton from glutamate 35, and aspartate 52 will stay deprotonated for the moment. So so we broke the glycan chain, right? So it left as a free hydroxy group, and as it left, we have a full carbocation behind. So it's an SN1 mechanism. Remember, an SN1 mechanism, the leaving group leaves first, so you get a positive charge. So let's continue with this SN1 mechanism. Then water will come in. The glutamate 35 will then remove the proton from water. We'll remove proton from water. And the oxygen from the water will attack the carbocation to regenerate this hydroxy group. And obviously this glutamate will regain its proton. So this is an SN1 mechanism. And there's a second possibility, an SN2 mechanism, where this aspartate now plays a role. All right, and so this glutamate will protonate this oxygen, and aspartate will attack this carbon in an SN2 fashion, right? So here the leaving group leaves first. Here the nucleophile kicks out the leaving group. That's why it's called an SN2 mechanism. SN1, SN2 mechanism. So this will form a covalent intermediate. Again, this will be a transient covalent intermediate. And then again, the glutamate 35 will capture a molecule of water, will activate water by removing the proton, and oxygen from the water will come in from the other side to give you the OH here, right? And regenerate the glutamate and aspartate. So as I mentioned, there's been a lot of debate as far as how this actually works, right? And currently the consensus of the community is that this works by an SN1 mechanism. Now the problem is it's virtually impossible to observe carbocations. Carbocations are such short-living species, right? So you can't really observe it spectroscopically. So you can't prove the existence of the carbocation. But for example, remember the main feature which would be different for SN1 and SN2 in terms of stereochemistry. Who remembers?
SN2 is inversion and SN1 is racemic.
Right. So good job. So in the SN1 mechanism, what one may expect is that when water is delivered to this carbocation, there might be some scrambling of stereochemistry, right? So the water can come in from the top, can come in from the bottom, and it's not entirely clear because the glutamate is kind of on top, so it may actually deliver water from the top, but it's not as stereospecific as an SN2 reaction. In the SN2 reaction, you can see the aspartate came in from the bottom, right? And so the only way for the water to attack this aspartate would be from the top. So this, so the SN2-like reaction would be entirely stereospecific, whereas SN1 reaction can lead to some scrambling. And so I think that piece of evidence finally makes scientists believe that actually this reaction proceeds through a carbocation, which is an SN1 mechanism. All right, so we out of time. There is a few slides for us to go through, which is enzyme regulation. Now, this is quite descriptive. You will see basically this is catalytic site, this is regulatory site, right? So let's say you have positive modulator, it binds at the regulatory site and it changes the shape of the catalytic site. And so the substrate can be accommodated now, right? If the substrate cannot come in here, the substrate cannot come in here, it can easily come in here after the positive modulator has bound. So this is the main idea for the allosteric regulators. So in the last few slides, there are just some examples of these regulators. We talked about some of these before. We talked about phosphorylation. We talked about acetylation of various enzymes. So this will be, in a way, some kind of half review for you, right? So basically, how these modulators can covalently or non-covalently change the regulatory site, and that will change the catalytic site. So I'll give you some pages to read for this. So 225. To 25. 235. And look at some problems I gave you in the discussion forum. And any questions about anything we've talked about today?
Yeah, you said for the lysozyme, it was NAG, and what was the other component of the peptidoglycan?
NAM, N-acetylmuramic acid, M, muramic acid.
Okay, thank you.
And then our next chapter will be on carbohydrates. We'll talk about carbohydrates. All right, so don't forget the sapling will be due on Wednesday, right? As usual, if you have any questions, you can stay for the office hours. You can throw in some comments in the discussion, and I'll see you all on Wednesday.
Thank you.
Bye, guys.